Give me a sec. I don't really like. Can you hear me?
Yes.
Yeah. Okay.
Yes.
Okay. Maybe I think I prefer using this instead of the headphones. Yeah. Anyway. Yeah. This is a very interesting invitation for me because it made me revisit things from quite a while ago. But also, just to remember that somehow this kind of this jump started my career after I graduated.
Hello, sir. How are you?
Okay, can you hear me?
Yeah, yeah.
Okay.
Yeah.
So
Hi,
you're busy,
Professor
man.
Kulkarni. How are you?
Okay. I
People are still joining. 10 minutes.
so I'm okay, except I have not been giving too many talks on Zoom. So I hope things
No,
work
but
out.
I think the slides you prepare, I think you prepare this sort of slide at every conference. So it is fine, whether Zoom or
Yeah, okay. Okay, I'm going to show you something. You can sort of see the faint thing, right? In gray and so on, right?
yes, we can see.
But yeah, you're not supposed to
Greater
see
than equal to 3, lambda.
But the definition is less visible. That definition Q greater than 3, it is in gray.
Correct. I mean, because I don't think I'm going to be able to write properly while speaking and so on. So I didn't want to risk making a mess. Anyway, I'm going to try this. Oops. Is it already? Let me see. You guys can see what I'm doing, right?
Yes.
Yeah. So I'm just going to sort of do things like that later.
So, sir, you did not take. I think you took part in that conference that you organized, right? That virtual, what they call it?
Well, I took part in it. I did
Gather
not
town.
organize it though. Yeah.
Oh, I
This
see,
is
I see.
yeah.
Okay. But that was fantastic, no? That gather town thing. I mean, that was.
Yeah. Okay, yellow is more difficult to see, right?
Yellow is not visible at all to me, at least.
Okay.
Yeah, it's very bad. I
You
cannot.
get black.
Yeah, no. I understand, but oh. Okay, let me go back to here then. But this has been a very ambitious program.
Oh my God, yeah, absolutely. Devendra and Professor Kulkarni sort of involved in it.
Right.
I also
Actually, yeah. I mean, there are many good talks, very interesting and tying things together and so on. So
yeah. So next semester, I mean, there will be lectures where I think I don't have much exposure, I would say.
right. So next semester is a little bit more number theoretic, right?
Yeah, more number, number theoretic. Yeah. Devendra, what is the plan for next semester?
Yes, formulas, question, background, and then developing the generalization where triangle groups and related curves appear. So there are some talks on the uniformization in February by Biswas, Kingsuk Biswas, and one Spanish woman, Pilar Baez, uniformization of Shimura curves.
I see. So Kingsuk has accepted.
Kingsuk accepted actually, and he will talking probably 15 February. And next week is the Pilar Baez from Shimura curve uniformization. I'm looking for this good speaker for this Majur who did related uniformization with modularity. So there are 6 slots available, so I will 6 more talks.
Talk to Jitendra. He may help. Jitendra, you know the subject well, no? I mean.
Hello. Yeah,
Jitendra, how are you?
Yeah, I'm good. How are you?
I'm fine.
Hi, Professor Kulkarni.
Okay.
Yeah, what you were saying?
So Devendra is looking for speaker. So I suggested him that you consult Jitendra. He is expert in this area.
No, I have got most speakers, 4-5 speakers. I just wanted to keep it open for a while. Sometime like in this trimester, we got some good speaker lately.
Oh, sorry. Can I ask a technical question? How long is the talk supposed to last?
1 hour with a break of 30 minutes.
Oh, so it's not 45 minutes or 50. It's
No, no, no.
No,
okay.
no, if you want to finish it in 45 minutes, it's up to you. I mean, I am fine with it. 45 minutes talk.
Well, actually, I really don't know how long it's going to last. So
Actually, one talk only, and yesterday we recorded a cancelled talk. So these 2 talks have finished in 30-35 minutes. Otherwise, people go speaking for 1 hour. Even some people speak more than 1.5 hours.
okay. Anyway, this I mean, it's a little bit like a expository, so it's good. If
Mostly
you have questions.
expository, yeah.
Yeah.
So I think, sir, I think the last time you gave a talk in India was in Benares, right?
Yeah, Varanasi. Yeah, Varanasi. Yeah. I was, I was thinking back, and I think my most interesting conferences have all been in India.
I see. That's great.
3 of them. Yeah. One in Almora for Ravi, and that was amazing. Almora, and then Varanasi, and one in Delhi. Yeah.
Overdue gave a talk in February also, right?
Oh yeah,
At Aisar Mohali.
That was at Aisar Mohali. Yeah. But that was virtual, no? So not physical in person. Actually, yeah.
Nandu, maybe you can start.
Okay.
Okay. So welcome everyone. So it's a great pleasure to have Professor Ser Peow Tan from National University of Singapore. So Ser works in the broad area of geometric topology, but as he mentioned at the beginning today, that this work, which was influenced by one of the, I think, great work of Professor Kulkarni, that actually helped Ser a lot to get the first breakthrough during his postdoctoral work, and somehow Devendra has convinced him to look back to it. Even though I hope that towards the end of this series of talks, Ser will be speaking about a much more recent work on some generalized modular groups. That is also very interesting, and it will be interesting to everyone, I hope. So the title of Ser's mini lecture series is Hecke Groups, Arithmetic and Geometry. So Ser, now it's over to you for the rest of the 45 minutes, 1 hour, whatever you want.
Okay. Thanks. I hope you can all hear me. Please speak up. Please feel free to speak up if you can't hear me. And actually, I'll prefer you unmute yourself and speak up, because I don't know if I can see if you put something in the chat. Okay, so anyway, it's a great pleasure to be here and to talk about Hecke groups, which was one of the things that I started investigating just after I graduated and came back to Singapore. And it was by tremendous good luck that I had a couple of very nice colleagues in Singapore who worked in number theory and algebra, and then we were trying to look for something, and by this tremendous good luck, we chanced upon this paper of Professor Kulkarni, an arithmetic geometric method in the study of subgroups of the modular group. So it was just one of those strange things, To be honest, actually, we first came upon an expository article of his based on this paper based on talks he gave, I think, in ICTS. And that paper was published in World Scientific, which is based in Singapore. And then for some reason, they were doing an exhibit or something, and we bought the book, and then there was Kulkarni's work. Yeah. So anyway, that really helped me jumpstart my career. Otherwise, there would have been literally no career. I was pretty much inactive for about 2 or 3 years after I graduated. So okay, So this is a very, very interesting paper of Professor Kulkarni. Investigated arithmetic geometric methods to study subgroups of the modular groups. And to me, the key observation was this one. Okay. He found the right fundamental domain for the modular group in terms of independent generators. Okay, so anyway, so I study hyperbolic geometry, in particular hyperbolic surfaces. So the thing that sort of interested me, of course, immediately was that so 2,3 infinity triangle group. Well, what can you say about the 2Q infinity triangle groups, which are the Hecke groups? Okay, so let me quickly explain. So I don't know if this is really the best thing to do, but I don't want to risk writing. So okay, so here's the definition, right? If Q is bigger than or equal to 3 integer, then lambda Q is 2 cos pi over Q. Then we have these two elements, S and T. Okay, S is just, of course, inversion about I, and T is translation by lambda Q. Then these two elements generate a discrete subgroup of PSL2R, which we call GQ. And this is basically a 2Q infinity triangle group. Now, if we look at the product of S with T inverse, this is R, then this is an element of order Q. Okay, it's a rotation about a fixed point with order Q, and so it turns out that we can think of S and R as generating GQ, and then S and R will be what we call independent generators for GQ, because S is a free product of the subgroup generated by S. Sorry, G is the free product of the subgroup generated by S and the subgroup generated by R. Right? So this one has order 2, this one has order Q. Okay. Okay, so here are 3 fundamental domains over here for the group GQ, okay, depending on which pair of generators we choose. This is the standard one, okay? So typically we use S and T as the generators, and then the fundamental domain over here consists of two triangles, and then T maps this vertical side to this vertical side, and S maps fixes this point and then rotates by pi, right? Okay. If I want a fundamental domain which reflects the generators S and R, then I need to choose this one. Okay. So here there are 2 copies of this fundamental triangle, but now they're glued along this side over here. And then in this case, again, S is S fixes the point I over here and identifies this side to this side. And then R fixes this point over here and identifies this side to this side over here. Right. So the main thing over here is that this one doesn't look nearly as familiar or as nice as this one over here. But on the other hand, the side pairings of this fundamental domain give independent generators for GQ. Of course, we could have used this one. This is if I consider this fundamental domain, then the side pairings will be T and R over here, and so this will be correspond to the pair of generators R and T. Okay. Okay, so I've just repeated that thing over here in a smaller thing. So I just want to talk about some basic facts of these Hecke groups. So the first thing is GQ is a 2Q infinity triangle group. I think maybe some people have talked about this. And here, what I want to emphasize over here is that it's a 2Q infinity triangle group. So it's just from this alone, you get a lot of geometry. Okay. The second fact, which is maybe quite interesting too, is GQ. I mean, just from the definition, it's obvious that GQ is contained in PSL2 Z adjoint lambda Q, right? because both S and T are in PSL2 Z adjoint lambda Q. So in particular, since this is a kind of a this is a nice ring, we have some arithmetic and number theory that can come into this into here. But this group itself is, when Q is bigger than 3, is quite nasty. I mean, it's non-discrete. So this is not a very nice group. And GQ itself, on the other hand, is rather nice. It's a maximal discrete subgroup of PSL2R. So we want to try and use both the discreteness as well as the fact that the entries lie inside this ring to and the interplay between these two things here. Okay, the third fact. Okay, I'm just going to do all of this. Okay, so the third fact is that over here is that okay, so first the definition, right? We say that X on the boundary is a cusp if it is the image of infinity under the group GQ. Okay, then there's a immediate fact. X must be inside the field Q adjoint lambda Q. Okay? Just because of the two generators. Okay. On the other hand, if I look at the hyperbolic elements of G and look at the fixed points of these hyperbolic elements, then a small calculation shows that X must lie in a quadratic extension of Q adjoint lambda Q. Okay. So this fact actually leads to something which I'm very interested in, but maybe I won't have a chance to talk very much now, which is determining the set of axes for the Hecke groups. Okay, so the fourth fact I want to talk about is that G4 and G6 are arithmetic. All the other Hecke groups are non-arithmetic. So by arithmetic, we mean here that they are actually commensurable to the modular group G3. Okay. So in some sense, you can think of it as almost like a comparable to the modular group. So almost anything you can say about a modular group, you can say about G4 and G6. Another fact which is quite interesting is that GQ, when Q is odd, is a Witch group. And in fact, all of them are, if Q is even, GQ is not a Witch group, but a subgroup of index 2 is a Witch group. Okay. So this is something I don't know anything about, but I thought was also very interesting because this means that somehow these Hecke groups arise in some natural way in some other context. Okay. So to continue on, the sixth fact is that GQ is actually a maximal discrete subgroup of PSL2 Z lambda Q. Okay. So like I said, most of the time when Q is, in fact, when Q is bigger than 3, this is a non-discrete group. But GQ, on the other hand, is a discrete group, and not just that it's maximal. Okay, this is not that difficult to prove. You can find this in Bearden. Yeah.
Can you remind me what is a Witch group?
A Witch group is okay. There's these things called translation surfaces, I guess, and then the Witch group is the group which sort of leaves this. Is a kind of the, how do you call? What's the word? It's
related to the translation surfaces.
Yeah. It's the.
I understand what is that. Okay. Okay.
Which is something which is very heavily studied.
Yeah.
At this point, so for example, if you look at the translation surfaces which are square tiled, then the Witch groups are going to be subgroups of the modular group.
Yeah. Okay.
But G5 is particularly interesting because G5, the Witch surface, the translation surface is very simple. Okay, so thanks Krishnendu for the question. Okay, the eighth fact is let me use a different color just to emphasize this. Is this theorem of Kurosh? Since GQ, any subgroup of finite index of GQ admits a set of independent generators in the sense of Rademacher. That means that you can find a subset Xi such that K is freely generated by the subgroups generated by Xi.
What about fact 7? Like G5 only we know and not other indices? GQ general.
Oh, sorry, I forgot. You see, I left out. So 7 is very interesting too. So 7 is, I'm going to talk more about the cusp set, but this is a rather remarkable fact that the set of cusps for G5 is in fact all of the rationals of all of Q adjoin lambda 5. Okay, and the only two times when, okay, so we call something like this sort of maximally cusp, because as I said before, the set of cusps lies inside this, but if it's everything, then we say it's maximally cusp. And in this case, G3 and G5 are maximally cusp, and all the rest, G4, G6 are not, and actually for the rest is not known. So somehow G5, we know exactly what the set of cusps are. So this is quite interesting fact. And not just interesting, it's a very useful fact too. Yeah. So that's why for that reason, actually G5 is my favorite Hecke group. It's sort of sufficiently different from the modular group, but at the same time, I think it has many properties similar to the properties of the modular group. Okay, so here are some. So here's the question, which is basically investigated by Professor Kulkarni in his paper, in his seminal paper. How can we find a set of independent generators for a given subgroup, for a given subgroup of GQ? Of course, if I need to be able to recognize this subgroup in some way, right? So what I would say is that if we can recognize this subgroup, if we can recognize whether an element is inside there or not. Okay. So this question was basically investigated by in that seminal paper in the case where of G3, which that's to say the modular group, and Professor Kulkarni gave a way to find a set of independent self-generators for any subgroup of GQ. Okay, so like I say,
these are some groups here are quite important for the non-congruence modular form, right? The one of the importance for G5 was also the first incidence when we started to see the unbounded denominator for the non-congruence modular forms.
That sounds interesting to me, but I'm afraid I'm not very,
okay.
Right. Okay. So in fact, there's another aspect to why we want to study this Hecke groups. I mean, which is this modular forms, or what they call non-congruence modular forms. But I don't know anything about it, to be honest. Actually, my collaborators from back in 25 years ago, this was in some sense also their motivation behind these things. I have to say one thing.
I see. Yeah, that's what yeah, okay. That's right. Nice. Yeah.
But let me tell you a story, which is that my collaborators, who were my colleagues in Singapore, were really trying to help me, establish myself, and they started work with me. And sadly, I have to say, unfortunately, all of them have retired. So I'm the only one left. So all of them have left mathematics, one way or another. So anyway, maybe that's why I'm giving this talk instead of one of the others. Okay, so here are a few more questions. Okay, let me just put all of them out. Okay, so next question is, which we alluded to earlier. Can we determine if some element of Q, lambda Q, is a cusp of a GQ or not. So this is in general quite a difficult question, except for those for a few special cases. Okay, so I'm going to tell you about a theorem with regard to this later. And then another question, of course, is, as I said, GQ is a discrete group. PSL2 Z lambda Q is a non-discrete group. So can we determine when an element of PSL2 Z lambda Q is an element? Actually, is actually an element of GQ. Okay. And then again, this last question, which I think is quite a difficult question, is can we determine the fixed points of the set of fixed points of hyper elements of GQ? So for this question over here, the answer is known in the case of the modular group, and this is a very classical basic number theory result that basically every quadratic integer every quadratic number is a fixed point of a element of the modular group. Okay, so but here the question is for the other Hecke groups, can we answer this? Okay, so these are some facts and some questions. And so my talk is going to be divided into 4 or 5 main parts. So I want to emphasize, first of all, the geometry. And then secondly, I'm going to emphasize some basic algebra. And then later, some of the arithmetic that comes in. And then later, the fourth part, I'm going to talk about the cusp, where maybe all of these things come in. The geometry, the algebra, and the number theory all comes in a little bit. Okay. So the first thing I'll talk about is the geometry. Okay. So let me take a break here and ask, are there any questions? Okay, if not, okay, so the geometry is my favorite part. It's actually quite simple, but there are several geometric objects to define, so you have to bear with me. And unfortunately, I couldn't draw very beautiful pictures. So again, I apologize for that. But so maybe before I even say anything, I just want to say that Kurosh's theorem in this case is really, it's a geometric theorem. Okay, it can be proven purely geometrically. It's got really nothing to do with the arithmetic or anything like that. Okay, so where does the geometry come in? Okay, so the first thing is that this thing is a 2Q infinity triangle group. So if you see this picture over here, this is a 2Q infinity triangle. And if you look at the group generated by the reflections, that's a well, sometimes called extended triangle group. But then now if we look at the subgroup of index 2 consisting of even, okay, that's a Coxeter group. If you look at subgroup of index 2, then that's actually the Hecke group GQ. Okay, so here are some objects that I'd like to define. The first thing is even vertices. Okay, so the even vertices are basically the translates of the point I under GQ. The odd vertices are the translates of this point over here. Okay, so let me emphasize this point over here. Which is a fixed point of the rotation under GQ. And then even edges are the translates of this thing over here. So this is a semi-infinite geodesic going from I to infinity, and then the translates of this are the even edges. The odd edges are the translates of this thing over here under GQ. They are colored blue over here, and then the finite edges these translates of this finite edge, that this finite geodesic arc joining the even vertex to the odd vertex. Okay. Okay, so I've tried to use a color scheme over here where the odd edges are colored blue, the even edges are colored black, and then the finite edges are colored green. Okay, and the even line. So as you can see, the even there are always two even edges passing through a even vertex. So they form a complete hyperbolic geodesic, and that's called an even line. So the translation of this thing is called even line. Okay. Okay, so this is just a picture of the fundamental domain. But what happens when we look at the image of this thing under the modular group? Okay. So what we'll see is something like this. The translates of this special triangle. So this thing is called a special triangle. This thing over here is called a special triangle. So the translates of this special triangle gives a tessellation of H by special triangles. But if we just ignore the blue parts and the green parts, then just look at the black parts, then we see the translate of the even lines give a tessellation of H by ideal Q-gons. Okay, so in the case for Q equal to 3, it's just ideal triangles bounded by even lines. All right, so there's this if you just look at the even lines, these black lines, then what we have is a very nice tessellation of the hyperbolic plane by ideal Q-gons, and this tessellation is invariant under the action of the GQ. Then if we just look at the translates, let me put this as green, of the finite H. So remember, finite H joins the vertex I to the vertex E to the I pi over Q. The even vertex, the odd vertex. If you look at the translate of this thing over here, it gives a bipartite cuboid tree. Okay, so I'm using the word cuboid with Q over here. In Kokanese language, this was a cuboid with C-U-B-O-I-D. But I think it doesn't. It sounds exactly the same, but that's okay, I think, because we're generalizing from tree to cube. Okay, so this is a bipartite cuboid tree embedded in H, and the even vertices have valence 2 and odd vertices have valence Q. Okay, so again, this tree, this bipartite cuboid tree is invariant under the action of GQ. Okay, so we can also, of course, think of this as just a cuboid tree. If we just ignore the even vertices, it doesn't really matter. But I don't know which is more convenient for applications. But okay, so this is just an observation, and then. This cuboid tree is dual to the ideal triangulation. So in particular, this gives us a way of measuring distances of of the ideal tessellation by Q-gons. So this gives us a way of measuring the distance of these Q-gons from the original vertex I. Okay, so we can define a level for ideal Q-gons. Where 2 Q-gons adjacent to I have level 0, and all other Q-gons adjacent have level. And for all other Q-gons, one of them has is adjacent to one with one less level, and the others have one more level. That's a mouthful, but it's not as difficult as it sounds. So maybe just let me show you some pictures. So this is a picture you get of a part of the tessellation of the plane by ideal pentagons coming from G5. Okay, so there's one pentagon here, there's one pentagon, here's the next level of pentagons, and so on. And then, as I said, the blue lines over here are actually the odd edges. Okay, they're not going to be very important for us for now. Then the green part is the finite edges, which will go on to connect into this bipartite cuboid tree. And as you can, so what we're going to, you can sort of, this is maybe easier to see from the picture. You can say that, okay, so here's the point I, right? So we said that these two polygons are at level 0. Then the next one's one further away will be at level 1, and then the next one will be at level 2, and so on. Okay, so that's all I'm saying about the level. So the reason why we want to define a level is that later when we do algorithms and so on, this will help us to get the algorithm going. Okay. Okay, so let me give you a geometric proof of Kurosh's theorem. Let me show you what. Okay, so suppose I have a subgroup of GQ of finite index. Then if I look at the tessellation of the hypoid plane by these special triangles, this gives me a tessellation of the surface which is obtained by the taking H mod out by K. Right? Okay. So you can think of this as that there's a tessellation on the universal cover which is invariant. Then you take the action of K and you mod it out. This gives a tessellation on the quotient surface. Or you can think of this as originally the original surface was triangulated and then you lift it, and since this surface S is a cover, we can lift the triangle to a triangulation of S. Okay, so we have this surface which has a tessellation by this ideal triangle, special triangles. The odd vertices on S which are regular, then if they are regular, that means that the total angle about there is 2 pi. Then we can remove all the adjoining odd edges. Okay. That means that if we remove all the odd edges, what we have is left is the ideal Q-gon. Okay. So that means that our surface is tessellated by ideal Q-gons. Oh, sorry. Ideal Q-gons and special triangles. Now the orbifold points of order 2 have exactly one even edge adjacent to it, and the orbifold points of order Q has exactly one odd edge adjacent to it. So what we can do is with this surface, we sort of cut away these special polygons. Sorry, we cut away these special triangles which are adjacent to cone points of order Q. What's left behind is something which is tessellated by ideal Q-gons. There might be some genus, so we cut it open, so it becomes a polygon. We put back the original triangles. So what it means is that after we cut open these edges, we obtain a fundamental domain. We have a fundamental domain for this subgroup K, consisting of ideal Q-gons plus a few special triangles, maybe none. Okay. And depending on how you cut it away, there are going to be side pairings for this fundamental domain. So the point here I really want to emphasize is this thing over here. Let me put it in red. By the Punkare polygon theorem, this particular fundamental domain will give the side pairings for this fundamental domain give an independent set of generators. So let me remind you a little bit what happens to the Punkare polygon theorem. You only get these extra relations if if you have vertices of finite. So your polygon, your fundamental, your domain is a polygon, which may have some finite vertices and some vertices at infinity. The relations come from the finite vertices. But over here, what we have is actually a picture like this. If I have a finite vertex over here, then of where this is pi 2 pi over q, then this side was identified to this side. So in other words, the relation that we get is actually exactly saying that the element over here, this side pairing, r to the q is equal to identity. If you have something like this where there's a order 2 point, again, the side pairing over here gives me something s square is equal to identity. All the other side pairings do not give me any relation. So all possible relations come only from the finite vertices, but the relations, because of the way that this thing was constructed, the relations were just of the form s square equal to 1 or r cube equal to 1. There are no other relations. So in other words, this actually gives a set of independent generators for K. Okay, so what does the fundamental polygon look like? It's an ideal polygon made up of several ideal cubons together with a number of special triangles attached to some sides of P. Okay, and what are the side pairings? Maybe I'll just. Okay, I'm sorry about this. Adjacent odd edges are paired. Adjacent even edges which meet at an order 2 cone point are paired. Now all other even edges actually are not meet at a point which is not a order 2 cone point, and they form even lines. And then the other even lines are paired according to how the surface was cut. Okay. So notice we have this fundamental polygon consisting of ideal cubons plus a few special triangles. And then the sides of the special triangles, the odd sides of special triangles are paired. Some of the even lines actually consist of paired even edges. All the other even lines are paired to each other in some pairing. So how do we encode this polygon and the side pairings? So let me just do it by example. It's maybe more illustrative than giving a lot of definitions. So in this example here, I consider the Hecke group G7. And then I suppose I have a subgroup K whose whose fundamental domain is given by this. Okay, so the fundamental domain consists of 1 7 gon over here. There's 1 7 gon plus 1 special triangle over here. And then there's side pairings. So this side over here is paired to this side over here. This side is paired to this side over here. This one over here consists of 2 even edges which are paired to each other. And this one over here also consists of 2 even edges which are paired to each other. And over here, there's a special triangle. So this side over here is paired to this side over here by order Q rotation. Okay. So we can encode this in what we call a Hecke-Ferry symbol. So what happens is we can write out the vertices of this thing over here. We start from infinity, which we write as minus infinity, then x1, x2, x3, x4, x5, x7, which is infinity. So first thing you know is that we can always choose a fundamental polygon which has infinity as one of the vertices. Okay. And then in this case over here, as you see, x1 to x7 is paired to x4 to x5. So x1 to x7 over here should be paired to x4 to x5. This is the reason we have the 1 over here. Then for x1, x2 is paired to x5, x6. So x1, x2 is paired to x5, x6 over here. Then between x2 and x3, half of it is paired to the other half. Okay, and we denote it by this symbol with a little o over here. Between x3 and x4, again, an even edge is paired to the other even edge, so we denote with this o. And then, so these things here were, the symbols were already written. And then the last one was x6 to x7. x6 to x7, we had a special triangle over here. So the pairing is pairing the odd edges. So we use this symbol, which is this blacked out bullet point. Okay. So when we cut open this to get a fundamental domain, we can always do it in such a way that infinity is one of vertices and 0 is another vertex. Okay, so we can always normalize so that this is true. So what we see over here is that xi plus 1 is an even line. It's always an even line. Okay. So now we can talk about Hecke-Ferry symbols. Next. Okay, so a Hecke-Ferry symbol is just a sequence of points. Okay, a sequence of points on the starting. We normalize so that the first one is minus infinity, x1, x2, in increasing order up to the last one is infinity. Okay, so these two are actually the same points. So this will be the vertices of the fundamental polygon, such that xi is equal to 0 for some I. This is a normalization. xi plus 1 is an even line. So in other words, you don't just pick any two arbitrary points. These 2 points must be an even be the endpoints of an even line. Okay, so in particular they are all cusps. Okay, each pair xi plus 1 is connected by a symbol. Okay, so either we have a symbol over here like this, empty bullet point, which just means that this thing consists of 2 even edges which are paired to each other. We may have a symbol like this, which is a solid bullet point, which means that adjacent to this even line there was a special triangle, and then the odd edges of this special triangle are paired to each other. Okay, or we may have a symbol like this, where we write integer a, and this means that this thing is paired to another pair with the same symbol a. Okay, so this will be saying that this even side is identified to another even side with the same label. Okay. Okay, so I hope this makes sense. So this is just a purely symbolic. I mean, like I said, this is pure geometry. I mean, it's true. It's just you can't actually do anything. You can't do any calculations. This is a purely geometric fact. We get this independent set of generators by looking at this special fundamental domains, and these special fundamental domains can be encoded by these Hecke-Ferry symbols. Okay. So so far it's purely symbolic, but if you actually want to do any computations and so on, then we need to actually be able to, write out the xi's in a form suitable for computation. Okay, so we need to be able to write the cusps in nice forms. Okay, so we'll talk about this slightly later, but before we talk about that, let me say something which.
Yeah, hello.
Yeah.
What is the form of the fairy-like property for consecutive vertices?
Consecutive vertices join even lines.
No, but in the modular case, it is this.
Yeah, so in a modular case, it will be like A over B, C over D such that the determinant is 1, right?
Yeah. So is there analog of that for the?
Yeah, very good. Thanks. I'm exactly this is the point I'm going to try and get to. A lot of our work was trying to find the analogous statements for these Hecke groups that you can make for the modular group. So I'll be coming to this very, very soon. But let me finish precisely. So if you just give me 10 minutes to you. But before that, let me finish with the geometric part of this thing, okay? Because dual to this thing is there was the bipartite cuboid graph, right? Okay. So this also is quite interesting. So let me just tell you what happens here. So in this case, the finite edge of F, so it leads to a bipartite cuboid graph on this surface. Right. So on the hyperbolic plane, there was a bipartite cuboid tree. If you take this thing, which is invariant under the action of GQ. So in particular, when I take this thing mod out by K, I end up with a bipartite cuboid graph. Because something's okay. Is that all right?
So this cuboid graph is a dessin, right?
It's not. I think so. Well, yeah. You know,
these are Grothendieck's dessin.
I should tell you the story about how lazy I am. Yeah. So maybe 2 or 3 years after I've been working on this, I met Gabino Gonzalez, who told me about Bailey's theorem and so on. And it was very interesting. And then he was trying to tell me that there should be some connections with this Grothendieck's dessin and so on. Exactly. And I think I agree with you. It's just I never explored this because like I say, I work on this for maybe 2 or 3 years, and later I sort of moved on to some other things. But I think this is, now that I come back to this, I think this is a very, very promising thing to look at. I agree. Yeah. So that there's so what we have is basically covering of the sphere, branch over 3 points, right? Except now instead of branch, in the case of a model group, one of them is branched by this tree, order tree, but now it's branched by order Q over there. But otherwise, it's pretty much the same thing. Yeah. Okay, so what happens here is the even vertices have valence 2 or 1 in this graph, and all vertices have valence Q or 1. And furthermore, this graph is actually, I think Professor Kokani is trying to say that it's a, I'm going to call you Ravi from now, okay? It's a bit easier for me. Okay. There's some design there, but you can think of this graph also as a ribbon graph. That means you can sort of thicken the graph a little bit. And so you think of it's like it's a surface. The graph is sort of the spine of a surface. So in particular, there's a ordering, there's a cyclic ordering of all the vertices, of all the edges coming out of the Q valence Q vertices. The boundary components of ribbon graph of this ribbon graph correspond to the inequivalent class cusp of H mod K. So I'm supposed to stop in. Or have I already gone over time? I've gone over time.
Maybe 10 minutes. You can speak and then take a break.
Okay. Let me finish this example and I'll take a break. Okay. Okay, so here what we have is this picture over here, right? Okay, so there was this graph which was dual to this thing over here. Oh, sorry. On the green. Right, there's this, and then this point was identified, this point over here, this was identified, this, and so on. So if I try and draw it, I'll get this picture over here. So the green thing that I've drawn is basically the graph, and then it can be thickened up a little bit, so it's a ribbon graph. So you notice that over here that there's this vertex over here, which is a valence 1, and so over here the thing just goes around here like this. This is a cone point. This is an order 7 cone point over here, and then but these two over here were the order 2 cone points coming from these two over here.
So without thickening, the right hand thing is that bipartite cuboid graph.
Yeah. So the green part, the green graph is a bipartite. It's a bipartite
Cuboid
graph. The red vertices are the even vertices, and the black vertices are the odd vertices. So in this case, there are two black vertices, one of valence one of valence 7 and one of valence 1, and then there are 1, 2, 3, 4. There are four even vertices in this graph.
Is it clear that what group it is related with? What finite index group?
You go this way, and then you can look at the generators.
Okay.
Okay. So I'm going to take a break before I go to the algebra, which will answer Ravi's question earlier, because for now, what I've said is all in some sense purely symbolic and it's geometric, and I can just use some kind of symbols. But we really want to have some algebraic manipulations, right? So I'm going to tell you about reduced forms and so on after the break. Okay. Sorry, so are there any questions for now?
Yeah. So is there any questions? So there is no questions, and then we go for break, and then maybe you start the algebra part after the break. Yeah.
Right, and that will be at what time again?
Yeah. So
Maybe you take 20-minute break to finish early because it would be night to your side.
Yeah. So a 20-minute break, is it?
Yeah. You want more?
Yeah. That sounds good. So it will be like 10 o'clock for me, right?
Oh, I see. Okay. So what is the time now?
No, not 10 o'clock. Sorry. I don't know why when I do this connection, I get a strange time.
What is the time now at Singapore, right?
Oh, yes, yeah, it's 7:23 p.m.
Okay.
How long should I have a break?
So maybe you start 7:50.
7:50, is it? Okay.
8 o'clock is better for you, or 8 o'clock is better for you?
I mean, it was announced to start at
5:30.
17, so I don't think it will be good for other participants.
Exactly.
We should start exactly what we have announced.
Yeah, so 5:30 Indian time, so 8 o'clock.
Which is 8 o'clock. Yeah, that's fine. Okay. Great. Okay.
Okay.
Yeah.
Maybe you will try to continue 5 minutes or little break.
No, I think it is okay. I mean,
Okay.
yeah. So we meet at 5:30 India time.
Okay, can.
8 o'clock
Okay.
Singapore time.
Okay, 8 o'clock. Yeah, can. Okay. Thank you all.